So hello everyone. Welcome to the, I believe, fourth week of the Stefanich-Tannaka Seminar. Today we have Alex, and Alex will be talking about the two category Groth ST comp, and we'll figure out what the category is. So Alex, please take it away. All yours.
Thank you. Well, first of all, thanks for speaking here. It's very nice. Very nice topic. So today, as already mentioned, we will talk about this thing here, whatever it is. But before doing so, let me give a recap because there's a lot of vocabulary going on at this point. So it might pay off to recall some of the principal notions that we had in the previous talks. Okay, so first of all, like probably the main building block so far, Grothendieck pre-stable categories. What was it? It was a presentable pre-stable categories such that filtered colimits commuted with finite limits. And we should really think about of them in the sense of like saying that a Grothendieck pre-stable category is something like the connective part of a stable category with a T structure. Having this, we defined the full subcategory on these Grothendieck pre-stable categories on PRL. And this nice theorem that was stated by Gustav last time was the Gabriel-Popescu theorem, which is the following, namely, if C is a Grothendieck pre-stable category, then this is equivalent to saying there is an A in E1 algebras in spectra, which is connective, such that C is a left exact accessible localization of A modules in spectra, but connective A modules in spectra. Okay, so just to say this will be a recap, and the recap will be me just sort of, showing you stuff I've already written down. And then after the recap, I will start actually writing stuff live. So it's not going to be this fast-paced for the full talk. So just to not make you worried. Okay. So also let me remind you that if C is a category, like a Grothendieck pre-stable category, then the spectrum objects on C, they inherit a canonical T structure such that the connective part is equivalent to C. And recall how did we construct this T structure? Well, we said, first of all, that the Spania-Whitehead category of C, it has a canonical T structure that we defined in, I think, Giovanni's talk. And then you take the right completion of that, and this will give you this category of spectrum objects on C, and also sort of the connective and the co-connective part along with it. Okay, so having all this, some more things. We also had this fully faithful inclusion of Grothendieck pre-stable categories into additive presentable categories. So there's this notion of an additive presentable category. Also, let me say once and for all, when I say category, I really mean infinity one category. I don't want to bother always saying infinity. So PRL additive presentable categories. So the category of those, and let me remind you that this is equivalent to the category of modules. So SPCN, so connective modules in PRL. This is because this thing here is something that is called a mode, so it's a classifier. So this is why you can write this thing as sort of modules over SPCN in PRL. Okay, and so this right-hand side has a symmetric monoidal structure, and it turns out that Groth, containing sort of the connective spectra and being closed under tensor products, so this Lurie tensor product, that Groth itself is symmetric monoidal, so induced by the symmetric monoidal structure on PRL at, and that this inclusion here is a symmetric monoidal functor. Okay, but what did we learn in the last few talks? We learned that Groth itself is a little bit defective. So one thing is it doesn't have all limits and it doesn't have all co-limits. That's sort of troublesome in some sense. So what we did was we restricted to only those morphisms which were lax, so co-continuous and lax, so preserving finite limits. And it turns out that if we had diagrams, so inside this category, then these categories in fact admitted limits. So these diagrams in fact admitted limits, and analogously, we had this notion of almost compact morphisms between Grothendieck pre-stable categories. These were those morphisms whose right adjoint preserved small filtered colimits when restricted to sort of these d less or equal to n, these co-connective parts. Okay. And And okay, again, I already said this, but these diagrams, so diagrams in here, they in fact admit co-limits. Okay. And so just to say this, well, of course we need limits, and of course we need co-limits. Co-limits mainly because we want to compute relative tensor products later on, right? Because they are computed as sort of this geometric realization, which is a co-limit over delta op. Okay, the recap is almost done, so bear with me. So another recall here is when C is a Grothendieck pre-stable category, then we can define the completion of this category C as just the limit of this tower of truncations. But this, as Gustav pointed out, is truncations in the toposphere sense, if you remember from last talk. And in particular, what we say is that C is called complete if the canonical map from C into this completion which is sort of just mapping X into the sequence of truncations, if this functor is an equivalence. Okay, so that was sort of this thing here. Let me remind you also that, well, this gave us this full subcategory on complete Grothendieck pre-stable categories, right? And we had a left adjoint to the fully faithful inclusion of Grothendieck complete categories into Grothendieck pre-stable categories. So this had a left adjoint, which is just this completion functor. And let me remind you, so why would we need this? Or let me first say some remarks. So the completeness condition sort of corresponds to the following, namely, if C is a Grothendieck pre-stable category, we know that we get a right complete T structure. But in particular, if our Grothendieck pre-stable category was complete to begin with, then this is in fact also left complete. So it's a left and right complete T structure. That was sort of one of the selling points. This is one of the selling points for this. Another selling point for this is that the completeness condition, it prevents this occurrence of something called phantom objects, which are non-zero objects that appear to be zero only if you look at the truncations. So every truncation can be zero, but the full object itself, it doesn't have to be zero. If you ask for completeness, then this goes away, this problem. And so this doesn't, so things that live in Groth comp are, for example, Q co X and the connective part of that. And the sort of, we will see this, but there is a completed tensor product, and this completed tensor product is the right intersection procedure that we will also see later when we actually get to Tanaka stuff. Okay, so this is sort of another proposition here that we did last time probably, is that sort of this left adjoint functor, this completion functor, is compatible with the symmetric monoidal structure. So in particular, what we get is that this category Groth comp with this induced monoidal structure is, so this is in fact a symmetric monoidal structure. Okay. And then almost done with the recap. So again, bear with me. So that's almost done. Recall also that if C is a Grothendieck pre-stable category, then you know we have the infinite suspension functor. And then this thing here, so C to SPC is in fact fully faithful. And the image of this thing is in fact what identifies the connective part of the T structure on the spectrum objects of C. Okay, and now almost done, like 2 more results, and then the recap is done. Let me also say, I don't know if this was proven in the last few lectures, but I think it was mentioned at least. So I gave the reference here if you want to see it. But so the statement is, if C and D are Grothendieck pre-stable categories, then we can consider this functor, which goes from L-fun CD, so left adjoint functors from C to D, into left adjoint functors from spectrum objects on C to spectrum objects of D. And the claim is that this functor is fully faithful. And the essential image of this functor is precisely sort of those co-continuous functors from SPC to SPD, such that F is right T exact. Okay. And okay, so from here, what we see is that Grothendieck pre-stable categories and their morphisms, what they encode is sort of really, you know, right complete T structures on these things, and then right T exact morphisms. Okay, so that's sort of the takeaway for now. And then there is a corollary that doesn't make sense yet, but will make sense in a bit, namely that this sort of assignment of C maps to SPC and then the connective part of SPC, which, I mean, this here is just C. This determines a fully faithful functor from Groth into something that is called Groth plus. This will be defined shortly. Okay, so this is the end of the recap. And now let me actually start writing, and I will write in white because maybe it's more visible. Okay, let me just get to my notes. Okay.
Just lighter color, please. Yeah, white. White sounds good.
Yes. Is this okay?
Yeah, that's
Okay.
fine. Thanks.
Okay. So what we saw is, so when we go back here, what we saw is that sort of Groth really encodes sort of right complete T, like stable categories with a right complete T structure along with right T exact morphisms. But the problem now is, so what's the problem? This is again still defective in some sense, because what we want is, so for example, if we have something like a morphism here, where X and Y are stacks, so X and Y are stacks, then usually I push forward, this will usually not be T exact. So sorry, right T exact, I mean. But it will be, so it will often be right T exact up to shifts. Okay, let me. Okay, so it will be right T exact up to shifts. I will explain what this means in a moment. So in particular, what we want to do, we want to enhance this thing here. We want to enhance this to account for morphisms that are right T exact up to shifts. Okay, so in order to do this, so this is sort of the motivation. We want to do this because we really need this, because I think later on when we have sort of maps of stacks which are quasi-affine, I think this is a sufficient condition for this push forward map between the quasi-coherent sheaves from X to the quasi-coherent sheaves on Y, for this to be sort of right T exact up to shifts, so up to, you know, shifting the T structure, like taking the connective part to the connective part on the right shifted by some integer n, you know. So we want to account for this because this is what we essentially need, or what we will need. So in order to do this, we have to keep track of sort of the connective part. And so the first step to doing this is the following, namely if C is a presentable stable category, then we can define a core of C.
By the
In the
way,
following,
I
yeah.
have an maybe not so relevant question, but and since you talked about like right T exactness, yeah, I just want to make it like get this clear. So
Mhm.
like I mean, usually like right T exactness is not something that you like always have, right? Like there, so F lower star, this can be like not right T exact for some T structure, but it can be right T exact for with respect to say the perverse P structure, right?
Mhm.
So like when does that happen? Like when is like it is not right T exact like usually like classically, but it is right T exact with respect to the perverse T structure.
So that's a question now, right?
Yeah, I mean like that's
Yeah.
probably not so relevant. You can maybe answer it later, but
Yeah, I don't know if
I've actually
I
heard
don't.
about this. So
Yeah, so I don't know if I have an answer for this. I mean, the motivation for us is really that what sort of, you know, it's not about switching between T structures. It's really about sort of sticking to the T structure that we have and then seeing that sort of most maps that we are interested in, they are not mapping connective to connective, but they are mapping connective to something that is shifted.
Right, right. Yeah, that's why I said it's not so relevant. But yeah, never mind. We
Yeah.
can talk about this later.
No, no, no.
Yes.
I'm happy. I'm happy to hear you.
Thanks.
Okay. 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 So what is a core? So a core of C is just a full subcategory C prime, and C prime is a full subcategory C prime, which is closed under extensions and colimits. Okay. So again, think C prime is something like, the connective part of a T structure. That's of course we don't really have a T structure yet, but that's of course what you should think about. So that's a core. You should think of the core as the connective part. And then we can have the following notation. The notation is the following, namely that core C is the poset of cores of C ordered by inclusion. Okay, so another thing, okay, so this is so cores is like any core of C is something like a prospective connective part for some T structure, let's say. And so what we now want to do is we want to make this core thing, this assignment core, so C maps to core C, we want to make this functorial. So in order to make this functorial, we have to say what it does on morphisms. So if if this is a morphism in PRLST, we want to get, so there is a canonical map from core D to core C. So how is this defined? Well, it maps a core in D, which we call D prime, and it just really maps it to the pre-image in D prime. And so you can check that this is still a core. So the pre-image of D prime is still a core. So you can check that this is well defined and functorial. And what this defines is this in fact gives you a functor from PRLST to, let's say, ordinary categories, like ordinary one categories. But let me delete this. Okay, let me just say, in order to make this rigorous, this goes to ordinary categories. And in fact, for this, it's fine to just define this on the homotopic categories. So you just only have to define it on objects and the one morphisms. And then because this is a left adjoint to inclusion, you can delete the homotopic category and just go to this and get a fully like infinity functor. Fully. Okay. Please interrupt me if there is any questions. I might go too fast sometimes. Okay. But so maybe you believe me now that there is a functor core from PRLST into cat that takes, as we said, and oh, sorry, this should be a contravariant functor. It should go from PRL up to cat, and it takes an object C, so a category C, and it maps it to the core, and the morphism is mapped to the pre-image, like it does the pre-image functor. And so now the Cartesian unstraightening of this functor. So this is a functor with values in cat, right? So we can unstraighten this functor, and we can define something that was mentioned on a previous slide, but we didn't define yet, namely Groth plus, and we just define this to be the Cartesian unstraightening of the functor core, and it comes with a canonical projection to PRLST. In particular, this thing, so let me just spell out this is a bit abstract, so let me just spell out what are its objects. So the objects of this thing are just pairs where one object C is in PRLST, the other object C prime is an object in cores of C. So this is, if you recall how the Groth deconstruction works, so just straightening and straightening, then you can remember maybe how objects in the Groth deconstruction or in the domain of the unstraightened functor looks like. And this is precisely what it is, like for objects. And you can convince yourself that morphisms, let's say from C, C prime to D, D prime, yeah, those things are precisely morphisms from C to D in PRLST, such that f of C prime is a subset or is a subcategory on D prime. So again, if you think about C prime as something like C greater or equal to 0, like the connective part of some T structure, and D prime to be something like this, then this really just means that, you know, the connective part is mapped to the connective part. So the image sort of makes sense, right? I mean, and so this category here, what it does, it's sort of the objects are pairs where you really keep track of the connective part of your T structure. That's sort of the idea of Groth plus. But again, we already said that just keeping track of the connective part of the T structure and then sort of functors that are right T exact. So this is really what right T exactness means. This doesn't do it because we want to allow for functors that are not only right T exact, but right T exact up to shifts. So we have to modify this core construction. So this functor core here. And we will do this in a second. Let me just do one remark on this construction, namely the following. So this functor f to the minus 1 from core D to core C, which again, you take a core in D and you map it to the pre-image under F, and this will be a core in C. This functor has a left adjoint, which we denote by F plus, which goes from core C to core D, and it maps C to to f of C, but then making these funny brackets, and the funny brackets mean smallest core in D containing f of C prime. Okay, so it's sort of the smallest core that has f of C prime contained in it, and this thing here will be, so it will be true that that f plus is a left adjoint to f to the minus 1. And so the thing that follows from this is that this functor Groth plus to PRLST is also a co-Cartesian fibration because it has sort of left adjoint transport maps along to the right adjoint transport maps that we had. And this sort of implies for you that in fact this vibration that we hear was initially just a Cartesian vibration, but because of these transport maps, it's also a co-Cartesian vibration. So in particular, putting both together, it's a bicartesian vibration. And moreover, what you will have is that note that PRLST and core C for every C, they have all limits and co-limits. So for PRLST, this is a well-known result for this core C. For this core C, the statement is basically that this is a complete lattice. So you always have infima and suprema. In particular, this means this thing has all limits and co-limits. Because limits and co-limits in posets are just infima and suprema. In particular, what this tells you is that because these are the fibers of this bicartesian vibration, and this is sort of the base of the bicartesian vibration, it in particular tells you that Groth plus has all limits and co-limits. So the reason for this is some proposition in higher topos theory, of course, like what else would it be? And the idea is, well, if you have a vibration like this, you can compute limits and co-limits by means of so you can compute limits by means of Cartesian transports if those preserve the limits. And then, you have an explicit formula for those limits, and then you can check that this is a limit. And the other way for co-limits, you use the co-Cartesian transports. And so I can write down the formula maybe if you're interested later. It's not really hard, probably well known to everyone here. Or if not, it's also fine. We can talk about it. So another thing that I want to say. Maybe I don't want to say it like this, or maybe I do want to say it like this. Let me see. Okay. Okay, yeah, let's do it. So if C and D are presentable stable categories, then there is a canonical map from C times D to C Lurie tensor product D. Let me denote this by the square tensor product. So this is this canonical bilinear functor that you get from the universal property of the tensor product. So from this tensor product, the Lurie tensor product. And so input what this thing here gives is that in particular you get some sort of functor, so some induced functor, namely you get a functor from core C times core D into core C times D. And this functor, it takes C and it takes D prime and it maps it to the hull of C prime tensors D prime. So this is sort of the smallest the smallest core in here, which contains the image of C prime and D prime under the functor here. Okay, so it's sort of the smallest thing that is generated from this bilinear functor. And in particular, what this gives you is that this functor that we defined here, namely this core functor, is a covariant. So we have to really take the covariant transports. So this is a covariant Lux symmetric monoidal functor. Okay, so you see this here, right? I mean, these are sort of the comparison maps that you have. And so you get a Lux symmetric monoidal functor. And okay, so let me do some, maybe this is not as obvious, but there's again some sort of unstraightening magic. And this, I think, so it wasn't obvious to me. But unstraightening magic yields that, so if you unstraighten this functor now, you also straighten along with it this Lux monoidal symmetric monoidal functor. So you unstraighten it as a Lux symmetric monoidal functor. I will get to what this means in a second, but the claim is that I can use some sort of unstraightening magic to turn this Lux symmetric monoidal functor core into a functor that is symmetric monoidal here. So this is a symmetric monoidal functor. So this here has the canonical symmetric monoidal structure, so a Lurie tensor product. But this here is sort of, we didn't know this before, but now we know this has a tensor structure. So this has a symmetric monoidal structure that is given as follows, namely tensoring is doing Lurie tensor products on the first component and then taking the hull of these things here, like we did before. And this gives you a symmetric monoidal structure. And the way to make this rigorous is sort of, okay, saying that this functor here is a covariant Lux symmetric monoidal functor, and from there you can do some unstraightening magic. And the unstraightening magic, yeah, either I say it now or I will postpone it. I don't know. Do you have preferences, or is it clear that this works?
Maybe say it
Maybe
now.
okay, yeah, let's say it now.
Thanks.
Okay, so yes, so there's the following lemma. So if C is a symmetric monoidal category, and in our case, C is cat, so but C is symmetric monoidal, then we have the following things, namely, we have that C alch on functors from C to cat with, okay, I will explain this in a second, but you can consider functors from C into cat, and you can endow this functor category with the day convolution tensor product that is induced from C and cat. And then you take commutative algebra objects on that. So quite funky. And and then on the other side, you can consider commutative algebra objects in co-Cartesian fibrations over C, but not with respect to the usual, like co-Cartesian fibrations over C have, of course, a Cartesian monoidal structure because fiber products over C so pullbacks over C are just sort of the Cartesian structure. So they are products in this category. But we don't take this category as the monoidal structure, so this structure as the monoidal structure, but instead we take something that I will also write as day, and it's sort of the transferred monoidal structure. I'll explain in a second. In particular, let me just remind you that there was this funny thing that at some point one reads in Lurie's book, namely that there is the straightening and straightening correspondence, which is this equivalence where you have functors from C into cat and co-Cartesian fibrations over C, and there is a mutual, like there is back and forth between those, and those are mutually equivalent. So this is the unstraightening functor, and this is the straightening functor. And okay, and so now the claim is that this equivalence, it induces an equivalence between commutative algebra objects, like this. And so it induces an equivalence between commutative algebra objects on the left and on the right. And let me explain the left-hand side first. So the left-hand side, so you can prove that, so this is sort of like, I don't know, are you guys familiar with the deconvolution tensor product?
Yeah,
Or
I
how?
think you can
Yeah, I
skip that
am.
part.
Okay, perfect. Let me just plug in my laptop so as to have more power. Yep. Okay, so there is this deconvolution tensor product. The cool thing about this thing is that on this hand side, we have Lax symmetric monoidal functors. So commutative algebra objects in here are Lax symmetric monoidal functors. And the morphisms are Lax symmetric monoidal natural transformations. Okay, so this is the left-hand side, and this just follows from C-alg just being algebras of, and this here. Okay. Okay, so this is some result in high algebra. I forgot the number, but this is in high algebra. We can talk about it later if someone wants to know. But the other side, and that's maybe the more interesting bit. So first of all, how to explain the other side. So this co-Cartesian fibrations over C, we have to endow it with a new monoidal structure. So what is this new monoidal structure? So for example, if we have a fibration here, we have a fibration here, let's call it phi prime, then this thing here by definition is the same as sort of you do the unstraightening of the whole thing, then you straighten phi, and then you do the deconvolution tensor product with the straightening of phi prime. So you just transfer the monoidal structure. It's sort of the cheapest monoidal structure that you can carry along the equivalence. So this will be a symmetric monoidal structure. And sort of by definition, algebra objects in here will be mapped to algebra objects in here. So they are in an equivalent correspondence, right? So this is really a one-to-one correspondence. But now on this hand side, you have a different interpretation of sort of Lax symmetric monoidal functors and Lax symmetric monoidal transformations. Namely, on this hand side, those things will correspond to C monoidal, or yeah, let me call them co-Cartesian fibrations of symmetric monoidal cats over C tensor, and co-Cartesian morphisms between them. Okay, So co-Cartesian fibrations of symmetric monoidal categories over C tensor, they are sort of symmetric monoidal functors from something which is a symmetric monoidal category into the symmetric monoidal category C. So the objects are here are really strong symmetric monoidal functors. So a lax symmetric monoidal functor on this side will be mapped to a strong symmetric monoidal functor on the right-hand side. And okay, so that's sort of the takeaway. So this thing here is a lax symmetric monoidal functor. So this here. But by the theorem that I just stated, this thing here will be a symmetric monoidal functor. And in particular, Groth plus will be mapped to a symmetric monoidal category. Okay. So it's a technical detail. So maybe I'll just keep going because there's much more important stuff to be discussed. But yeah, let's postpone it for later if someone has questions on this. I'm happy to talk about it. And yeah, okay. So let's believe the magic for now. And let's say that, yeah, okay. Didn't want to do this. So now what we want to do is modify core. How much time did I use? Okay. So modify core. So how do we modify core? We want to keep track of like also functors that shift the T structure. So what we will do is the following. Okay, and also please interrupt me if something is unclear. I'm very happy to answer questions. Okay, if C is a presentable stable category, then we can equip core with a new equivalence relation, namely C prime is less or equal to C prime prime if and only if there exists an n in the integers such that C prime is a subset on the n-fold suspension on C prime prime. So the image, let me shift this to the other side. Okay, so C prime is less or equal to C prime prime if and only if there exists. So this is a definition. There exists a
Sorry,
natural.
I'm sorry.
Yep.
Shouldn't the suspension be on the opposite side, or?
It doesn't matter.
Oh
It
yeah,
doesn't
yeah, it
matter
does. Yeah,
because you
sorry.
can, yeah,
Right,
you,
right,
you
right.
can just, yeah, you can just apply to both sides sigma to the minus n because it's the demand is that I think it's just more natural to write it like this. So Stefanich does it the other way around, but I think it's more natural because I don't know. I just like it better. So it's something like this, right? Um, okay. Yeah. Let me not do it.
Sure, makes sense.
Yep. Okay. So now what we will do is we can define core and then quotient it out by this equivalence relation. So this will be the set C prime such that okay, no, that's bad. I didn't want to write it like this. But okay, so this is just the collection of equivalence classes of core C under this equivalence relation up here. And if C prime is a core, let me write C prime for the associated equivalence class in core C. Okay. And in particular, we note that this here is a poset with respect to the less or equal to. Okay. So this is a poset with respect to this less or equal to. And now we have the following construction, which is analogous or very similar to the previous one that we had. Namely, we will define this functor, which we denote by rho, which should be a functor from PRLST to cat, which maps a C into core of C and then quotiented out by this equivalence relation. And let me also say that if we have a map F, so first of all, oops, we should get a map like this. So now I want to do the covariant case first, and let me also denote it by, let's say, F plus. And so what does this map do? Well, it maps an equivalence class of C prime to the equivalence class of the hull of f of c prime. So it maps it to the equivalence class of the hull of f of c prime. Okay. So similar to before, but now we have the equivalence classes. Okay, and also let me say immediately that just like before, there is another functor which is f to the power of -1. And this functor, it takes an equivalence class and it maps it to the equivalence class of f to the -1 of the thing. And this is also well defined. And in fact, we will again have that f plus is left adjoint to f to the -1. In particular, what we now do is we define this category Groth and an overline, and we define it to be the co-Cartesian or Cartesian straightening, it doesn't matter. I mean, with regards to this functor rho that we defined up here, so rho is just this new label for this functor that maps C to the core C and then equivalence relation. And this is a canonical projection to PRLST. And just like before, this is a bi-Cartesian vibration. Okay, so but now sort of the cool thing that happens, because we said that we didn't keep track of we wanted to also allow functors that shifted the connective part of the T structure. But this is what we established now, because first of all, objects in here. So the objects in here are sort of pairs C in PRLST and an equivalence class C prime in core C equivalence, right? So this is sort of just the objects and the morphism from here into there is simply a morphism F from C to D in PRLST, such that there exists an N in Z, such that F of C prime is a subset or a subcategory of the D, so n-fold D suspension on D prime. Okay, so that's sort of what we wanted to allow. So again, you should think of this as sort of, f of c greater or equal to 0, and then is a subcategory on d greater or equal to n. So that's what you should think of. So it shifts the T structure by n steps. So this is what we encoded with this. And let me make a remark here. So this category Groth is only finitely complete and co-complete. And the reason for this is that core C equivalence relation, those have finite limits and co-limits. And so why do they only have finite limits? They only have minima and maxima, sort of for finite things. And you can see this because, well, the very definition that we had is there exists a finite integer. There exists a finite integer, and because so if you could construct a sequence where n goes to infinity, and this cannot be sort of contained in this category, and so this is where you run into troubles. So it can only have finite limits and finite colimits. Okay. And in particular, what this means, so by sort of the same argument of computing sort of limits and colimits in the unstraightening of some functor, this thing here has finite limits and finite colimits, sort of by the same argument that we did for Groth plus. So maybe there is some questions at this point. Okay, there's no questions. So either I have silenced you into I don't know. Okay, obedience or something. So let me keep going. So we also have the following thing. So we have this functor which we denoted by rho, and it's this functor here. And what again we do is that this is a this is a Lax symmetric monoidal functor, just like before. This is a Lax symmetric monoidal functor, and we see this as follows, namely if Ci and D are elements in PRLST, and F is a functor from C1 times Cn to D, let's say multilinear. So multilinear meaning co-continuous in each variable separately. Then what we get is we get a canonical map from the cores of Ci, but equivalence relation. So from this product into the core of D equivalence relation. But so what are these mapped to? So these I must make the equivalence thingies. Yep. Equivalence brackets. Sorry for my bad handwriting. It will get worse probably. But you should remind me if it gets unreadable.
It's very readable so far.
Okay. So this sort of this map that is induced here, it's just taking sort of this n tuple of equivalence classes, of course, and it maps it to the hull of the image of f of all these Ci primes, and then taking the equivalence class of that. Okay, so that's sort of this map, and this sort of tells you that this is in fact a Lax symmetric monoidal functor. But if this is a Lax symmetric monoidal functor, we can again do the Grothendieck magic, the straightening and straightening magic that I alluded to before. And oh, here I actually wrote it down nicely, maybe. Okay, it's the same thing. Again, let me just write down what we get. We in particular get that Groth is symmetric monoidal. And so it's a symmetric monoidal category. And we also get that the canonical projection map to PRLST. This is, so this thing here is a symmetric monoidal functor. And moreover, so let me just be very explicit with this. So if we have C and we have an equivalence class C prime, let me say what this tensor product in here is. So what's the tensor product in here? So the tensor in here, it's you take C and then this equivalence plus C prime, you take D and the equivalence class D prime. And this thing here is again just the Lurie tensor product on the first coordinate. And then on the second coordinate, you take the equivalence class of, you probably guessed it, just taking the equivalence class of the sort of image of the multilinear functor, then taking the hull of that and then the equivalence class of this. So just like before, but again, the thing that is in here is sort of this extra equivalence class relation. So it really just sort of everything is sort of compatible, coherent, blah, blah, blah. Let me also say, yeah, now this is bothering a little bit. So let me delete this.
So this means that this functor is like co-Cartesian morphism between these operats, I guess.
Yes, so exactly, yeah. So or sorry, what did you say? Maybe I misunderstood.
Yeah, no, I think this symmetric monoidal functor between Groth bar and PRLST. So it is seems like it's a co-Cartesian vibration of operats.
Yeah, exactly. It's a co-Cartesian vibration of operats, but sort of the operats are symmetric monoidal categories.
Right, okay.
So it's a special, yeah, it's a co-Cartesian vibration of operats. Yes, exactly. Yeah.
Thanks.
Okay. Yeah, maybe I should also mention, so what's the unit object? in Groth and then bar. Well, this maybe might not be too much of a shocker, but it's SP and then SPCN, so the equivalence class of that. So that's the unit object in with regards to the tensor product. Okay, great. So how much time? Okay, I think hopefully we'll be going. Sorry if I'm going too quickly. I'm really sorry. Is the speed okay, or should I? Because it also doesn't make sense if I'm blasting through too fast.
I think you're doing good. I think.
Okay. Okay, thanks. So another thing that we now have is, so we constructed two functors, right? Two, in fact, Lax symmetric-conoidal functors. We constructed this functor core, and we constructed another functor, which we called rho. And there is a canonical Lax symmetric-monoidal natural transformation here. And so how is it given? Like on components, let me not write rho C, but let me write core C and this. Well, this is really just sort of the quotient functor. So you map C prime to the equivalence class of C prime. This is a functor. And in particular, well, you can check that this is, well, yeah, right. You can check that this is, let me just write it down a little bit. You can check that this is a Lax symmetric-monoidal natural transformation. So that something like this is true.
Sorry to interrupt, but could you please not use this color?
Ah, yes, sure. You know, the nice thing about this is that I can always do something like this. Is this better?
That's
Okay.
fine. Thanks.
Okay. Yeah. Okay. Um, okay. So that this diagram here commutes, so the canonical diagram like this. Um, so remember, these were these comparison functors that we had before. And okay, so well, you could convince yourself that this is in fact a Lax symmetric monoidal natural transformation. And by the above theorem, or by this straightening and straightening magic, this gives us a functor from Groth plus to Groth bar, which, so this is this functor C is mapped to SPC and then C. Yes. And wait, what did I want to say? Okay, yeah. So this is this functor, and this functor is in fact strong symmetric monoidal. Okay. And this follows from sort of this here being a Lax symmetric monoidal natural transformation. So this is again this sort of straightening and straightening magic. That Lax symmetric monoidal functor natural transformations will correspond to strong symmetric monoidal functors. Or
Wait a sec. So do you mean like from Groth to Groth bar, or
yes, sorry. Yeah. Yeah.
okay? Thanks.
Yeah. I think so. Um wait, do I mean let me just check just to be sure.
Yeah,
Maybe I
because if you
confused.
say Groth plus, it's like a pair of objects, right?
Yeah, exactly. It's a pair, but yeah, no, it has to be this. Yeah, sorry. Oh wait, no, sorry. I just wrote the functor wrong. Um, yeah, I think I wrote the functor wrong. It is a strong symmetric monoidal functor, but I think the thing that I wanted to write, sorry, because otherwise it doesn't make sense, right? It should be Groth plus, and the reason it should be Groth plus, it should be some C which is stable, and then some core here, and then this just maps this into the equivalence class of this. Sorry, I was just
Yeah,
this is
yeah, that makes sense.
Yeah. Sorry. Thanks for catching that. Yeah. Thanks for catching that. I confused myself there. Okay. So having all this, we can now finally go towards this Groth ST comp. So we now do the first step. So this will be a definition. We do Groth ST, and we define this thing to be the full subcategory on Groth things. So these are pairs, and then an equivalence class of a core. And we take the full subcategories on the objects that look like this. Okay, so we take only those objects which are the stabilization of some Grothendieck pre-stable category, and then we sort of fix the connective part to be just C. So this is sort of a core. C is definitely closed under extensions, and
Alex,
and
sorry to
yeah.
interrupt. Sorry to interrupt.
So
Yeah, can we please go back again? So I think like the function that you'd written. So yeah, this is fine, but like the thing that you'd written before that, even that was okay. Like if so, you have like this. So you have this map from symmetric monoidal embedding from Groth to Groth plus, right? So the function that you had written that was also okay. I think so. I
yeah, that's true. So
right?
the functor that I wrote is also symmetric monoidal. That's true. So you
Yeah.
can also go from Groth to Groth bar. But what I wanted to write down and is this functor.
Yeah,
And
yeah,
sort
yeah.
of rigorously writing down this functor follows from this remark.
Right,
Yes,
right.
thank you. You again caught me. So very very nicely done. Um, okay. So what else did I want to say? Okay, so just to reiterate, so we have this Groth ST. Groth ST is the full subcategory on objects of this form, where C is a Grothendieck pre-stable category, SPC is the stabilization of C, and the equivalence class of this Grothendieck pre-stable category C. Okay, so we take only those objects. And so then we have a proposition. And I think I will not have time to prove it, but it's sort of just a technical thing. I don't think it's that important. Um, so I'll not prove it for now, but maybe we have enough time to do it in the end. So imagine that you have Grothendieck pre-stable categories C and D, and imagine that you have an equivalence, so some fixed equivalence from this one object on the left to this other object on the right. Um, and this equivalence, of course, it makes sense in Groth ST. So this full subcategory that we just defined here. And so suppose you have this, um, then the statement of the proposition is that then C is complete. So let me remind you, this is sort of that this canonical map here is an equivalence if and only if D is complete. Okay, so the statement is sort of completeness is invariant under equivalence in Groth ST. Oh, and I should really write complete here. I didn't complete the word complete, so that's kind of funny. Okay, let me. Okay, so the proof is not too hard. I think it's a bit annoying, but it's yeah, it's combinatorics, let's say. So let me skip it for now. Maybe we can talk
Which
about
which
the
is
stuff.
why it's annoying, right?
Yes, yes, yeah. Um, okay, so now having this, so now this is sort of saying, yeah, so that this completeness condition, at least in Groth ST, is if stuff is equivalent, then the equivalent stuff is also complete. So what we can define then, or what makes sense to define, or let's say notation, I guess, is we can now define this ominous Groth ST comp. And we again do it as a full subcategory on Groth ST on the objects SPC C for which C is an object in Groth comp. So the complete Grothendieck pre-stable categories. So we do precisely what I said. We just again restrict to the full subcategory on those things where C is now where the connective part is now complete. Okay. Mm, Okay, so how much time? Okay. Yes.
Alex, you have 32 minutes.
Okay. Thanks. Thanks. Um, okay, so another proposition that we have now. So and now we defined all this mess, and we sort of defined another like full subcategory Groth ST comp. And of course, like because sort of by the very definition, this thing here is a fully faithful embedding into Groth ST. So you could now ask, is there a left adjoint, right? I mean, that's always like, is this a localization? And this is of course true. And so this is the statement of the next proposition. And let me do this. So C and D. So let's D be an object in Groth comp. And let P denote this canonical functor into the completeness, like the completion of C. So this is the canonical map. What we then have, so the first claim is, so let me say statement one. Statement one says that map, so whenever I write map, I mean the hom anima. So map is always hom anima, and when I write something else, like I guess hom or more, then I will mean something categorical, like hom categories or something like this. This will come later. So I'm getting ahead of myself again. But so if I have maps on like the mapping anima on Groth ST comp, um, and I take SP C bar, so this completion of C, and then the equivalence class on this thing. And then here, let's say SPD and D. So note again, D was assumed to be complete. Then now we have a canonical restriction functor given by SP of P. So P was, again, P was this map here. We do SP of P, and then we precompose. And where do we land? Well, we land at maps in Groth ST. And now here there is SPC C to SPD, and then the equivalence class on D. And also let me say that in the Stefanich paper, at some point Stefanich just stops writing SPD and just writes D and then D. And so I think, yeah, he's just lazy, but I will just uphold the standard of always writing SP. Okay, to make it more, yeah, visible, let's say, or more clear. Okay, and so the statement is that this here is an equivalence. So that this precomposition functor is an equivalence. And this is, of course, just saying that, this object here is the left adjoint applied to this. Like this will give you the statement that, in fact, we have such a left adjoint. And the second statement of the proposition is the following, namely, okay, so that let me call. So we have this inclusion functor. And then as we just said, there should be a left adjoint. Let's call this left adjoint LST. So the existence of this is sort of justified by LST of SPC C being sort of this thing here. So this is by definition what this thing here is. So I'll just leave it there to see for you again. Okay, so this is the left adjoint. This follows from one. And the statement is that so this left adjoint is compatible with the symmetric monoidal structure on Groth ST. Okay. And okay. Yeah, so let me see. Yeah, let's prove this. Let's prove this to be industrious for once, because I think I didn't really prove anything yet. So let's do it. So first of all, we want to prove statement one. So we want to prove that this map here is an equivalence. So how do we do this? So we do this as follows. So we remember that these things here, so this functor category is really, so this is, okay, wait, I should go. Yeah, let me just write it. So I claim that it suffices to prove the following statement. Namely, for all n, yeah, for all integers n, we can consider the following full subcategories. So we consider the full subcategory on the functors from SPC complete, so from L-fun SP of the completion of C to SPD, and such that those which are right T exact up to an n shift, so shifting by n. And so we have this side. And on the other hand, so what I claim is that this here is equivalent to L-fun SP SPD, f of C being, oh, and I shouldn't, sorry, I mean, I think what I really want to write here, this is of course a bit of a nonsensical thing, but this should be SPD, right? Okay. So I claim that it's enough to show this. Well, if it's enough, well, if you sort of take the union over all those for all n, then you get everything, and same on this side. So if you can show that those sides are always sort of equivalent as categories, you show that everything is an equivalence as categories. But now there's this neat trick, namely we shift the T structure on SPC. So we just shift it. We just apply the shift functor to everything. We just shift our core, the equivalence class of our core. And what we get then is that or let's say we shift those full subcategories. So then we may reduce to the case n equals 0. But now the funny thing comes, namely, we know that Groth comp, this is the inclusion of this into Groth. This is left adjoint to this completion functor. But, well, we have already seen that okay, so my claim is that this thing, this adjunction, so this here, whoops, this being a left adjoint to the inclusion is the case n equals 0. And the reason for this, let me go back. Sorry for the scrolling. I hope you don't get dizzy. But the reason for this is this proposition that I stated. Namely, if C and D are in Groth, then there is a fully faithful functor on morphisms in Groth from CD into the left adjoint functors from SPC to SPD, which are right T exact. And so let me go back again. Sorry again for scrolling. The statement for n equals 0, so if n is 0, then this just means this is right T exact functors. Right? So you go into right T exact functors, you go from right T exact functors to right T exact functors. And so this is sort of just the universal property of this completion functor. So this takes care of one. Okay. Let me now do 2. So for 2, so now we know that LST exists. They should have called it LSD, but yeah, that's a miss there. So this functor exists. And so now we have to show that this is compatible with the symmetric monoidal structure. So namely, what does this mean? We have to show that if we have a morphism like this, then let's suppose this is LST local. Then what we have to show is that F tensor with the identity, which should be a functor from SP C tensor E. So for some E, yeah, so for some E, for any E, E is some other like Grothendieck pre-stable category. That is okay. And so we have to show that, yeah, this is horrible, but sorry for that. That this canonical map, like so, that this here is also LST local. So this is what compatibility means. So compatibility of a left adjoint with the symmetric nodal structure is just saying, well, you take a morphism that is LST local, so that is local with respect to this left adjoint localization, and then you tensor by some object, in this case SPE, and then the equivalence class of E. And if this sort of tensoring still preserves the LST locality, then your left adjoint is compatible with the symmetric nodal structure.
That is stability, right? Is a stable under tensor products.
Yes, that's being stable under tensor product, sort of. Yeah. But so there is then this theorem by in high algebra that tells you that this gives you, so this condition, if this condition is satisfied, then in our case, Groth ST comp will have a symmetric nodal structure that is induced from Groth ST. Okay. Okay, so the following now holds. So first of all, if F is such a morphism, we can consider the following diagram, following commutative diagram. And I'll tell you in a moment what it is. So here we have LST of F. And here we have this diagram. So my claim is this diagram commutes. And this is SP on P. So P, yeah, let's call it PC, for where PC is the canonical projection to the completion. And on the other side, we have SP of PD. Okay, so what we note here is by assumption, because F is LST local, this thing here is an equivalence. On the other hand, SPD, these functors here, they are LST local by 1. Because, I mean, why are they LST local? They are the units of, these are the units of the adjunction. So the components of the unit of the adjunction. So the left adjoint will send them to equivalences as well. So this is LST local. So in particular, we can reduce to show that tensoring with SPE and then the equivalence class of E preserves LST locality of F being equal to SP of PC. So we can reduce to the special case. So why is this the case? Well, if we tensor this whole diagram, so if we tensor this full diagram with this here, and this claim is true that that tensoring like this specific F being SP of PC with SPE and the equivalence class of E, then sort of this will, so that you have to think of the tensor here, like a tensor with E here, and tensor with E here, tensor with E here, right? So this here will always be an equivalence because this was an equivalence to begin with. And if this is SP local, this will be SP local if, right? I mean, if the claim holds for this thing here, being stable under tensoring, then this whole thing will be LST local and this whole thing will be LST local. And therefore we have a composition of LST local things. So this thing here is also LST local. So this will prove the general claim. So we can restrict to this case where we just check LST locality for F tensor ID, where F is now the specific morphism SP of PC. But for this, we can again do the following thing. Namely, we can consider them another commutative diagram. Okay. So we can consider another commutative diagram, and this commutative diagram is, so we go from SPC tensor E, like here, to the equivalence class, and we go into SP completion of CE. Oh, sorry, I have to make it smaller. I think it wouldn't fit otherwise. And then the equivalence class of this completion of C with E. And so let me just remind you, or let me just note that this thing here on the top, this is the same as SPPC, tensor identity, bimonoidality of this tensor product. So you can identify this morphism with this thing. And then you have vertical maps. And the vertical maps are just, again, the completion functors. Like, the completed tensor product. And here also the completed tensor product. Okay, so let me just, maybe the notation is a bit heavy now. Let me just say this thing here is this, and then a big hat. Just to make abundantly clear what this little symbol here means. And then we go into C hat, and then tensor hat E, and then here C hat tensor, and then tensor E. Okay, sorry, this is a very messy proof, or at least heavy to write down. So we have that bottom map here is this. Yes, is there a question?
Yeah, sorry to interrupt. Could you maybe go up a bit?
Sure.
So what is this like SPPC tensor
Sorry, what do you mean?
So like here, like we're taking this, like on the right hand side, on the right hand corner of the square, like should it be the class of C completion tensor E, or like yeah,
So this,
I guess you can do that. We are just like identifying.
yeah, so this here should be C, so that the completion of C, then tensoring with E, and then taking the full completion of the whole thing.
Right. No, I don't know. It's the second object that I'm talking about, but second object of the pair. But I guess yeah, you just use the monoidality. I guess.
Yes.
Right. Okay. Great. Thanks.
Um, okay. So where was I? Mhm. Okay. Yes, okay. So now the claim is the following. So we know that this thing here is SPPC, and then here this times identity. But this here, so this thing here is this map. But so now that the funny thing about this is an equivalence, and Y is an equivalence. So this bottom horizontal map is an equivalence because the map from Groth to here. So first of all, this is symmetric monoidal. So what we get is that this, yeah, shouldn't delete this, but this is the same as this, right? So you have this thing here, and this symmetric monoidality applied with this thing here, because PC is of course also L local. So L local, maybe I should write this here local, meaning that this whole thing is an equivalence. So the bottom thing is an equivalence. But so now this thing here is LST local. This thing here is LST local because it's again the units of the adjunctions. And so, right. So, and this proves the claim, right? Because we have LST local, and an equivalence. So this thing here is LST local, but because, sorry, this is a lot of colors now, but because this thing is LST local, um, uh, this thing here will also be LST local after tensoring, so it holds for every f. Okay, sorry, this was too many colors. Sorry for this. I hope it was a little bit clear. So any questions on this? So this proves the claim. And it was probably very confusing. Sorry for that. Okay. I'll just keep going then, if there's no questions. Um, so now we come to the statement that we talked about before. Sort of, there is a canonical functor from Groth to Groth ST, which takes C into SPC and then the equivalence class of C. So this is this, and this is symmetric monoidal, but in particular, this induces a symmetric monoidal functor from Groth comp to Groth ST comp. Okay, so that's the claim. So in particular, this functor here is symmetric monoidal, and it's the same functor. Right. And so this is also symmetric monoidal. And the proof is short, but let me not do it because I want to do the two categorical structure and I have 10 minutes left, right? Is that fine, 10 minutes or?
Yeah, it is exactly 10 minutes.
Okay, okay. Okay, so two categorical structure on this graph. So we now constructed this graph ST comp. And so we want to have this as a two category. And Gustav said he now likes two categories very much, so I will indulge him and give him a two category. So first of all, I mean, why two cats? So we will see this in the next talk, but we need it for something called almost rigidity. Um, so I'll leave it at that, but that will come next talk. And now let me recall the following thing, namely, cat is as a category is compactly generated. So what does this mean? Well, you take the full subcategory on cat on the compact objects. Then what you will have is that the int completion of cat omega will be equivalent to cat. Okay. Or let me say it differently. The canonical functor from the incompletion into cat will be an equivalence. Okay. And what do I want to say here? Yes, okay. So what we want to do is we want to realize this thing here as a two category, and in particular we also want to realize Groth as a two category and Groth ST and all the variants that we had so far. We want to have them all as two categories, just in case. So there will be lots of two categories. And so now what we want to do is we want to do the following. Okay, yeah, we want to do the following. We want to take a category I, which is compact, and we want to map it to I tensor SPCN. So let me define what this means. This really is the same as taking pre-sheaves on I and then tensoring. So pre-sheaves on I is now a presentable category, and then tensoring with regards to the Lurie tensor product and tensoring it with connective spectra. But again, this is the same as just computing with the Lurie tensor product, so using the explicit formula, this is the same as functors from I up into SPCN. Okay. So this is just a formula of Lurie tensor product. Okay, having this, what we get is, so the way we define this, if you look at this, so taking pre-sheaves is also a symmetric monoidal left adjoint. So this is a symmetric monoidal functor in particular. So it's a symmetric monoidal functor from cat to PRL from to PRLL, just PRL. And then tensoring again with SPCN is again also co-continuous. So and a symmetric monoidal functor. So in particular, we get a symmetric monoidal functor as follows. So we have this canonical inclusion, which is symmetric monoidal. Then we have taking pre-sheaves, which is symmetric monoidal. Then we go into PRL. Then we tensor this with SPCN, just like we did before. And then we go into PRL add, like the additive presentable categories. And in particular, it turns out that this here factors in Groth. So you will have a factoring in Groth. So by factoring, I mean that this diagram here commutes. And so in particular, the full composition, yeah, let me make it green. The full composition will be the functor that I denote like this. So just by abuse of notation. So this is the functor, just like before, that takes an I and maps it to this thing here. Or more aptly put, to the SPCN valued pre-sheaves on I. Okay. And it again, it factors over Groth. Because, well, if you take pre-sheaves of SPCN, then SPCN gives the Grothendieckness, like the Grothendieck pre-stable, blah, blah, blah. It will carry this on to the pre-sheaf category. Okay. In particular, what you will have is that, this is symmetric monoidal. Oh, bad color, sorry. This is symmetric monoidal. Okay. 5 more minutes. Yes, so I will make it hopefully. And so in particular, also, let me say, it preserves finite colimits. So why only finite? Well, we cannot really speak for more because this thing only has finite colimits, right? So we ask that it preserves finite colimits, and it really does. So this preserves finite colimits. And in particular, what we get is that for C and D in Groth, we can define a functor from cat omega op into a category of anima, which we call now. So now is the time where I write more instead of map. More Groth CD. And we will define this as a functor from compact objects on cat up to anima. And we define this as the functor I maps to, I shouldn't make the arrow that long. Map Groth I tensor SPCN and then tensor C to D. Okay, so for fixed C and D, we constructed such a thing and sort of because this functor that we had here, like the functor upstairs, this preserves finite colimits. This functor here preserves finite limits. And now we remind ourselves of one more fact, namely that, so we know that cat is equivalent to the int completion on cat omega, but the int completion on cat omega is the same as lex, so left exact functors from cat omega up to ani. Okay, and so in particular, what happens is that our morphism object will live in sort of these left exact functors, and in particular, this thing here therefore lives also as a category. Okay, so we have constructed a morphism category from this nonsense, and the idea is mainly, okay, so this means Groth is tensored over cat, and so let me say closed tensored or something. In particular, yeah, okay, there is some references that tell you that, if you have nice and rich categories, then you can define them as such things as well. Like, okay, this is of course not a one-to-one correspondence between enriched categories and those things, but any such category that is closed tensor, it gives you an enriched category. Okay. In particular, what we get is we get that Groth will be a two category. Okay. So that's sort of one thing. But so for this statement, what we really only used so far was that this here preserves finite colimits, right? Now let me change to a funkier color. But we also have that this thing here was a symmetric monoidal functor, right? And so, yes, so it turns out that because this thing here is symmetric monoidal, it will turn out that Groth is in fact a, okay, let me not write C alch, but let me write C mon on 2cat. And the way to see this is, well, you want to, how much time? Okay, sorry, a little bit. Is it fine?
It's fine. You can take extra 5 minutes.
Okay, thanks. Sorry. So in order to define the two-categorical structure, you would have to say that this is a symmetric monoidal two category, and in particular, you would have to construct such a map. So that's the action of the tensor product on morphism categories. And in order to construct this, in order to construct this via symmetric monoidality of so I spelled this out in some detail in the notes. So I will upload my notes afterwards, but I don't think it's necessary to do this now because maybe you can believe me at this point.
Sure.
Okay. And so and now what one can do is you can do the same things to the other stuff. Well, instead of considering SPCN, you replace this by a functor that I denote by the tensor stable and then SPCN. And this is just given as, the functor from cat omega to Groth. This was SPCN. And then from here we go into Groth with this canonical thing, C maps to SPC and then C. Right? And so this functor here, it again preserves finite colimits. And plus is symmetric monoidal. So you can also show this because this thing here is symmetric monoidal and this thing is symmetric monoidal. And in particular, what this will induce is in the same manner, Groth ST will be a commutative monoid object in 2cat, so a symmetric monoidal 2 category. And similarly, what you have is, you remember the localization functors. So this was this completion functor from Groth to Groth comp. And you also remember the localization functor LST from Groth ST to Groth ST comp. And when you consider, instead of the previous functors, you consider LSPCN or LST, so ST SPCN. So these are, again, they preserve finite colimits and symmetric monoidal plus, so finite colims, so plus symmetric monoidal. In particular, they will induce symmetric monoidal structures. So they will give you that Groth ST comp and the other variants. Let me also say this and this, that they are commutative monoids in 2cats. Okay. And yes. Okay. So there's a final remark. Yes, okay. So let me go out here. Maybe. Wait, why is it not working? Okay. It just doesn't want me to go out. Okay. So final remark, and then I'm done. I'm sorry for going over time. So the final remark is as follows, namely, you have that, you go from SP, you have this canonical projection map from SPC and then the core of C, the equivalence class of the core of C. This is symmetric monoidal, and it's a functor of symmetric monoidal 2 cats. Because I mean, this is a two category and a symmetric monoidal 2 category with the Lurie tensor product and just a 2 category structure that is in PRL, ST. And on morphism categories, we get oh my gosh, I'm sorry for the brackets. Okay, so on morphism objects, you get an equivalence. So the action of this functor. So this functor here, action on morphisms, is the following. So it's an equivalence. So the essential image of this thing, I mean, this is sort of what we expect, and I think what we already know. But f is right t exact up to shifts. And of course, this again includes into L fun. So you will get a fully faithful embedding on morphism categories. That's sort of the claim. And in particular, what you will get from this is that if you have a functor like this in your category Groth ST, then this has a right adjoint in Groth ST if and only if the right adjoint is, so it's a morphism again in Groth ST. That's sort of the thing that is such that the underlying functor is a right adjoint to the thing, and the right adjoint itself preserves colimits. So it means that if there exists a right adjoint, so let's call this F, and F is a functor from SPC to SPD. So the statement is there should exist a right adjoint from SPD to SPG, which preserves colims plus T exact. So right T exact up to shifts. And the really, really last claim, and that's it, is that a square in Groth ST is vertically right adjointable if and only if the verticals, so vertical arrows, admit right adjoints. And so right adjoints in Groth ST. And the underlying square in PRLST is right adjointable. So the last condition is sort of, if the underlying square is right adjointable, then the Beck-Chevalier condition is satisfied for the square. That's everything that's saying. Okay, sorry, with that out of the way, this is the end of the talk. Thanks for sticking with me.
So let's thank the speaker first, and then we're open to questions, I guess.
Yeah, sorry for going over time.
Okay, so are there any questions? We also have a post-recording session, so if you don't want to ask your question now, you can talk about it to Alex later. Okay, so if there are no questions, let's thank our speaker again, and I'll stop the recording for our post-recording session, presumably.